Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Christopher Ferrie. He is an associate professor at the University of Technology, Sydney, and the Center for Quantum Software and Information. He is the author of several books, and today we're going to focus on his latest one, Quantum BS, how to ruin your life with advice from quantum physics. So, Dr. Ferrie, welcome to the show. It's a big pleasure to have you on.
Thanks for having me.
So, first off, tell us, what does quantum mean in physics? Because I'm sure it has a specific meaning, and then people, particularly charlatans, tend to distort the meaning of the term, right?
Yeah, I mean, it's like many words. It can mean a lot of things. So it can be used, as an adjective, a noun, a verb, right? But for me, I think the core is quantum physics, and quantum physics is like a branch of science, uh, probably including general relativity, like one of the most recent branches of science, even though it's now 100 years old. And it had its roots in trying to understand atoms and subatomic particles. But today we understand it a little bit differently. It's the branch of science that applies to highly isolated systems. So anything that you can isolate really well from an environment requires this new physics with its own equations and set of laws and language that surrounds it to accurately describe. So if you have some highly isolated system, there's no environment around, and you want to predict what will happen to that system, and you don't use quantum physics, then you'll probably get the wrong answers. So if you think about an atom, maybe you've heard like, you know, you're mostly empty space, or a table is mostly empty space. That means like atoms, they're really, really tiny, and the space between atoms is huge, and the internal parts of atoms are really small, and the space between those is huge. So they're just isolated from everything that's around them, and that's why quantum physics is required to describe them accurately.
So this is more of a, I guess, psychology question, but as a physicist, where do you think misunderstandings about quantum physics stem from?
Well, there's probably a lot of answers you could give to that question. I think primarily it's because quantum physics involves mathematics beyond what most people would be exposed to. So if you've taken a little bit of mathematics in high school, probably around the world, everyone's required to take some level of mathematics. And then quantum physics, at least the basic version of it, requires just a little bit more than that, right? Your first or second year of undergraduate science or technology or whatever would prepare you to understand the mathematics of quantum physics, but that's not what most people have. So often these quantum concepts are explained using metaphors and analogies to make them more accessible to, everyday people. Um, that can sometimes be helpful, but it also results in like some oversimplification that leads to misinterpretations. So, it once that gets mentioned in like popular culture and media, then like these oversimplifications uh, get sort of amplified, and the focus ends up being on how mysterious quantum physics is with reference to these oversimplifications, when it's actually quite simple. It's just, a set of mathematics that you would learn if you had done a few extra subjects in school.
So, I mean, I would imagine that if people just use the term quantum in a colloquial way with a meaning different from the meaning it has in quantum physics, and they didn't attach it to quantum physics itself, you wouldn't have a problem with that. I mean, the problem you have here is that not only people use the term quantum, but they are referring to quantum physics phenomena and concepts, and then they are misinterpreting them or abusing the terms and the concepts to sell BS, right?
Yeah, I mean, Quantum's a word. I mean, it doesn't belong to us. Anyone can
Yeah.
use it. I mean, I use these dishwasher tabs that are branded as quantum. I don't believe that they involve, some, more nuanced aspects of quantum physics, but they work really well. So, I use them, and I don't mind that they use the word quantum.
So, I mean, but when it comes to selling stuff that is BS, what would you say are some of the main strategies used by the charlatans? I mean, they pick on a particular quantum physics concept or term, and how do they go from there?
Yeah, I mean, it's not just charlatans. It's
Yeah.
also just, I mean, TikTokers that want to pretend like they know something
Hmm.
about the universe and become an influencer. I think there's just so much information um, that it allows people to latch on to the things that feel good for them. So in terms of like the main cognitive biases that are at play, I think confirmation bias is the most important one. So, people will search for and remember the the videos or the things that they hear that confirm to their pre-existing beliefs. So if you have this, feeling or suspicion or whatever that uh, something will vibrate with your chakras, then if someone comes along saying, well, quantum physics is about vibrating with chakras, then you're going to latch onto that because of confirmation bias. Um, and then the other one, which is a bit problematic, is the appeal to authority. So you often see some of these oversimplifications and these misinterpretations repeated by reputable outlets, media, even scientists themselves who are being a bit lazy and will say things that aren't necessarily true, which often isn't that big of a deal. But when it comes to quantum physics, people can run with those misinterpretations and extend those analogies beyond, well beyond the realm of usefulness.
So let's go through some quantum physics phenomena and talk about what they really are and then how people tend to distort them. So, starting with energy, what is quantum energy and how do people tend to distort the term?
Yeah, I mean, so energy itself, of course, has like a colloquial meaning, right? Um, in physics, it has a very sort of concrete meaning. So, uh, if you can just Google it or look it up on Wikipedia, energy is the thing that causes changes in systems. And it takes various forms, many of which probably the listeners have heard of: kinetic energy, potential energy, thermal energy, chemical energy, nuclear energy. There's all these like real physical forms of energy. And you've probably also heard it, at least in high school or maybe even elementary school, uh, you know, the core mantra of science: energy can never be created or destroyed. So we all learn energy comes from the sun. It gets transformed into chemical energy through photosynthesis and yada, yada, yada. Eventually, kinetic energy happens when we start to move our bodies. Um, so that's like classical notions of energy from physics.
Right.
Quantum energy uh, is probably the first concept that was understood within quantum physics. And what it says is that energy doesn't change continuously. So I can't just change the amount of energy a system has arbitrarily. So if you imagine lifting a weight, a rock, in the air, it will gain gravitational potential energy because the higher I lift it, the more it's going to smash something below it, right? So the higher I lift a rock, the more potential energy it has, the more energy it could release when I let go. And I could change it by any amount I want. I could move it just a tiny little bit or a lot, it doesn't matter. I can raise it and lower it any amount. But in quantum physics, the energy can only change in very well-defined discrete chunks. So rather than, say, moving a weight like on a slide, it has to move in steps or on like a ladder. It can
Mhm.
only be at certain places and never in between. It's very, very subtle, like that the steps in quantum energy are tiny, so tiny that it requires very expensive experimental equipment to actually move them yourself. That's why we can't notice it in our everyday life. But in the real world, in the quantum world, energy doesn't change continuously. Like on a slide, it changes by steps. Um, I think the people often just attach the word quantum to energy without actually using the correct concept of it.
Mhm.
So they want to use this colloquial definition of energy, like it's some vague thing associated with feelings or like vitality or strength or power, um, some invisible force that permeates the universe, right? Um, Completely non-scientific, can't be measured, has no basis in anything that we can observe. And to make it sound more interesting, they often put the word quantum in front of it, completely sidestepping the the core concept of quantum physics, which is that energy can only change discretely. By the way, like when it changes, right, it has to have given energy or taken energy from somewhere. So that amount of energy is called a quantum, and that's where quantum physics, the word quantum physics comes from.
So, what would be an example of a product you've seen people trying to sell while applying the label quantum energy to it?
Sure. So, like you know, a, a fairly mundane example that I saw recently was something called a quantum therapy bed, and it it it's it's like a massage therapist bed, but it has attached to it this kind of arm that hangs over the bed and has a bunch of lights. Well, it has seven lights: red,
Hmm.
yellow, green, blue. It has the sort of standard spectrum of lights,
Yeah.
and the lights are shaped like crystals. And inside, like embedded inside the crystals, are like herbs and spices and I don't know, essential oils or you know the standard sort of alternative medicine stuff. Uh, but they're just LED lights. They're like Christmas lights. And it, it's quite expensive because I mean it's an interesting piece of engineering. It's a standard massage bed. It raises and lowers. But it has this extra arm, and you can program it. There's like an app you can program it with. It's not sold for consumers. It's sold for people who have alternative medicine practices. And the the pitch is take your alternative medicine practice and give it like a so-called quantum upgrade because then you'll be able to dupe your own customers better because you have a quantum light therapy bed. Um, but of course, it doesn't do anything physically, right? It's just a bunch of Christmas lights attached to a standard bed. Um, a more serious example is something called the Quantum Zeroid Consciousness Interface, which I think has changed its name several times. But it's like one of these EEG type machines, so like a medical scanning device. You take little electrodes that have little suction cups that attach to your body, so you stick them to your body, and then you plug those into an electronic device, and there's like little displays that have lines that wiggle and stuff. Uh, so it's meant to, I mean, an actual device would detect electrical signals that are present on the surface of the skin of your body. Um, which of course, which there are many, right? Um, but this device doesn't really do anything beyond that. Like it detects subtle electrical signals on the surface of your skin, which is not that difficult to do. But then it tries to interpret those in like BS language, like quantum energy profile, and give you like fake numbers, like, oh well, if your profile number is 7, then you need more rest, or right. It's just random signals and then interpreted with extra BS language on top of it. There's nothing quantum about it, but the recommendation is you stick the things on your head because that's where consciousness is. And so you can make it seem like it sounds more important than it is. Now, the problem with that device was it was well marketed, and about 20,000 units were sold in the US, including to US hospitals. And there were a couple recorded cases of people dying from using them, not because the device actually harms you, it doesn't actually do anything, but because those people were convinced that it could cure a very serious disease that required medical attention, and they used the device in lieu of medical attention, and then died. So that device is now banned from the U.S., and the person who created it is a fugitive that is living in somewhere in Eastern Europe, I think.
Yeah, it's
Still selling
interesting.
it. Yeah.
Still selling it. Oh my God.
Yeah.
I mean, I was just going to comment that it's very interesting to notice that many times pseudosciences or charlatans, I mean, their practices intercept. Like, for example, you get pseudoscientific claims about physics or quantum physics more specifically, and then they intersect in this case with alternative medicine that is, as far as I know, for the most part, not really supported by any good evidence. So, I mean, there's sometimes that interception, right?
Yeah. When I was doing research for the book, I was ready to actually kind of strain my brain trying to really figure out, the nuances in these things. But for the most part, the word quantum and then various terms from quantum physics, like quantum energy, or probably things that we're going to discuss later, like superposition and entanglement, they just get attached on
Yeah.
without really any second thought or detailed. There's no relevance to actual quantum physics. It's just the words that get attached on because they seem more legitimate, like they seem like they legitimize or create the illusion of complexity, right? So of course, the idea is you you tell people that. I think the easiest way to convince someone of something is that you're smarter than they are, and you're an expert, and they're not going to understand. But there's a lot of people that do, Nobel Prize winners and stuff. So some people understand it. So don't worry. It is well understood. So now you can trust me that my you know my seemingly miraculous claim is actually grounded in science. It's just something that's too complicated for you to understand. So I think that's why quantum physics often enters into these things, is because you require that illusion of authority and complexity that's beyond comprehension. And I think people mm, like that. They've you know they some people have legitimate problems, right? And sometimes medicine can't help them, uh, and so they're often quite desperate, and maybe it feels like something miraculous needs to happen in order for them to be saved or helped, and so this comes along, and it sounds pretty good.
Right. And what about the term quantum leap? because I mean we hear it quite a lot coming from some pseudo-scientists, and also I mean sometimes just people in general when they would just would want to say something like, "Oh, we're taking a big step." Instead of that, they say we're taking a quantum leap, or there's a quantum leap occurring here. So, I mean, does it have any specific meaning in quantum physics?
Yeah, so because this energy only comes in discrete chunks,
Hmm.
if you obtain energy or give away energy, uh, it's a discrete event. So it's like you've leaped up a step in energy.
Yeah.
So in quantum physics, I think they're originally called quantum jumps
Hmm.
uh, when you change your level of energy, and then that turned to quantum leaps. So I think the term legitimately comes from quantum physics, the idea that if there's a discrete change in something, then you've taken a jump or a leap. Now, the problem is like if you try to quantify with numerical values what a quantum jump is, it's like zero point 0 followed by 24 more zeros and then a 6, right? So quantum jumps are tiny. Nevertheless, it does mean that you've avoided a continuous transition and then jumped. So the colloquial use of the term is meant to mean some some discrete change, some jump has happened. Oftentimes, it's referring to it's meant to refer to a big jump, right?
Hmm.
So some technology changes, you go from version 1 to version 2, and you say, we've taken a quantum leap. Um, or, yeah, something happens societally or technology broadly in technology, and we say there's a quantum leap, right? So ChatGPT represents a quantum leap in technology, something like that. I think is okay. I'm willing to accept it. I'll allow that. It's a not terrible analogy to quantum physics. It's like in classical physics, everything is continuous. You expect energy to change continuously. If you want to go from one state to another, you have to do so continuously. But in quantum physics, you take these jumps. So that was sort of a paradigm shift. So now we want to have an analogy to other things in our everyday life. It's a pretty good analogy. It's not the worst case of quantum BS. So like I said,
Okay.
I'll allow it.
Okay, good. So, and what about waves and particles? I mean, in quantum physics, are they two separate things or are they the same?
Well, so classically, waves and particles are separate things, right?
Okay.
So when we learn about classical physics, we often talk about particles when we learn like Newton's laws. So uh, you do this in high school. You calculate the trajectory. You say if I throw a ball, it's at this speed and at this angle. How far away will it land? These are the sort of calculations that you'll have high school students do. And you treat the ball as a particle, like it's a point, not something that has extended um, volume in space.
Hmm.
It just makes things easier. So particles have like a location, they have a specific point in space. Waves, also an intuitive concept, right? You've seen water waves, ocean waves. You can't point to where the wave is, right? It's extended in space. So these are two completely different things. So classically, they're separate things. Quantum mechanically, there's neither. There's neither waves nor particles, not physically. Uh, we use analogies
Hmm.
to create like simplified models or things that allow us to talk about them and communicate with them. So, we say words like atoms or quarks or photons uh, or electrons,
Hmm.
and we say that these are particles. But that's just to help us. We have to say something, otherwise we can't communicate at all. But that's just to help us identify the phenomenon that we were talking about. And there's a wave equation. Well, I mean, there's an equation. It looks just like the equations used when we solve wave equations in classical physics. So we call it a wave equation. Things oscillate. So we call it a wave equation, but it's just something that helps us calculate the expected results of experiments. So there are no real waves, there's no real particles. There are a set of equations that allow us to predict the outcomes of experiments, and sometimes we like point to things in those equations and we call them waves or we call them particles, but that's just to help us communicate with a common language about what we're talking about.
Yeah, and I mean, before asking you a little bit more about that, I guess that this already points to the limitations of our language when talking about quantum physics phenomena, and trying to understand how things work, right?
Yeah, I mean, within the physics community, there's no issue because, when I say electron to another physicist, that person knows what I'm talking about,
Right.
what equation I'm referring to and what parts of the equation I'm referring to. So there are I mean, this is a problem in all branches of science or anywhere where, there is highly technical jargon being used. So when I say price or when I say cost, these are actually really technical concepts in economic theory. But even the average person can kind of connect it to something in their everyday life. The problem in quantum physics is like these words that we use are connected to these things in the equations that not everyone is familiar with.
Mm-hmm.
And they'll often instead connect it to some other intuitive concept that's not really connected to quantum physics. And that's kind of where the problem lies, right? It's, we have a language to describe quantum physics very accurately. It's not in the language that everyone is happy to listen to or speak, right? It's some complicated mathematics. And if you speak that language, then you can use shorthands, everyday jargon and words and things to refer to those more complicated things. And that's fine if you know them. But if you don't know them, you end up connecting them to things that are pretty far removed from the actual correct thing.
Right. And I mean, when it comes to waves, there are people that seem to have tried to invent diseases based on waves, like wind turbine syndrome or electromagnetic hypersensitivity. I mean, I have to tell you that before reading your book, I'd never heard of these invented diseases. But
Yeah.
what are people claiming here?
Yeah, I think it's more of a sort of a Western society problem, luckily. Um, e- Especially in North America, where um, often things get attached to political movements.
Mhm.
So lots of things are politicized. So, um, anything to do with alternatives to coal energy is is automatically politicized and attacked. And it doesn't take long for someone to invent some conspiracy theory surrounding these things. Um, I don't know the origin, but I can, I see it happening, so I know who perpetuates them.
Mhm.
It's often there's a phrase, I don't know how it translates in other countries. I got it from Canada, where I'm from. It's called busybody. Um, so it's somebody with too much free time that just look, they imagine a person sitting in their house and looking out and just complaining about everything that they could possibly complain about. You know, somebody doesn't cut their lawn, so you call the city council to complain about that, right? Somebody doesn't hide their garbage bins, so you call this city council to complain about it. Somebody trying to just, you know, be be the neighborhood police. Um, and so when they hear something like, oh, the wind turbines, they're dangerous, or Wi-Fi is dangerous, then they quickly latch on to these things and start writing emails or start making newsletters or start petitioning schools, because just they have way too much time on their hands, and they feel like they need to complain about something. So I don't know where it originated, but I know how it's perpetuated. I can tell you that there's no like basis behind them because the list of ailments that these things are supposed to cause is just unending. People just invent for every problem that they have, they blame it on uh, well, whatever's around them. For example, you know, wind turbines can cause you know, cancer. They can cause whatever problem you might have, depression. They can blame it on these things. Now, if you've ever stood under one, uh, it it is loud, right?
Hmm.
It's quite annoying. I wouldn't want one on my property. It's a kind of a bit of an eyesore.
Yeah.
But I also wouldn't want to live next to a freeway, or a busy road, which is also noisy. But nobody's complaining about those because they've been around a long time and they're powered by the coal industry. So there's nothing to complain about there. Um, the Wi-Fi thing, again, people say, yeah, mm, you know, the electromagnetic signals uh, cause diseases of all sorts. Of course, there's no evidence for that, and uh, you know, sometimes it's very similar to the whole autism is caused by vaccines thing,
Hmm.
right?
Yeah.
Again, it's confirmation bias that comes into play, right? Um, you you know, very rarely, but also occasionally, um, you know, a child is diagnosed with autism, and that's very unfortunate. Uh, in some small cases, that was immediately preceded by a child getting vaccinated, but you know, lots of people get vaccinated. In fact, I'm hoping the vast majority of people get vaccinated, right? Yet they don't develop any sort of disease afterwards. So
Yeah.
um, it, it's this sort of confirmation bias, and then you get a few celebrities or people with loud mouths that talk about it, and that's what gets latched onto. Because nobody tweets, "Hey, I just got vaccinated and I didn't get autism," right? Like people don't do that. So there's this selection and confirmation bias at play, and the same would be true of wind turbine syndrome, or or you know, I don't even remember, electro hypersensitivity disorder, whatever it is, right?
Hmm.
Um, you know, there's a Wi-Fi port right next to me, right?
Hmm.
It's not a problem for me, but I don't tweet about that not being a problem. But if somebody comes along and says, "Hey, well, I feel like I remember the last three times I had indigestion, it was because I was next to my Wi-Fi router," and then they just latch onto that and
Yeah.
run with it. And I think the problem in the social media age is that for every little niche, you can get a lot of positive feedback, right? So if I tweet something provocative and negative, it's more likely to get engagement than if I tweet something benign but true and accurate.
Hmm.
And you know, people like that feeling. They like that feeling of being included, involved, part of something. And I think that's why these things get elevated
Hmm.
to the extent that they are, is because of that positive feedback that people feel when, you know, they get a little heart on their post on Twitter or Instagram or wherever it may be.
Yeah. So tell us now about the uncertainty principle, because that's another one that has been sort of appropriated by popular culture, at least to some extent, and I think that many
Mm.
times people distort this principle.
Yeah. Uh, but it actually it just occurred to me that like on the topic of like the waves, I just wanted to mention, right,
Oh, okay.
for the listeners who might not be aware, right? So scientists and engineers have spent a lot of time figuring out what ha what frequencies of waves, depending on what phenomena you're talking about, are harmful to the human body. So when you think about sound waves, those are pressure waves in air. Of course, the human body is susceptible to sound waves. That's how we can hear, right? So
Right.
our eardrum resonates with a certain set of frequencies, and if you put a lot of power into those frequencies, then it can damage your ears. If you've ever been to a concert, you'll find out the next morning that maybe you shouldn't have stood next to the speakers. The whole body is resonant to about 10 hertz, so that's below what you can hear with your ears, but it's because whales are giant, they actually communicate in that frequency. Um, so you can play, like if you Google play at 10 hertz, then there's a YouTube video that will play a 10 hertz tone, even though you can't hear it with your ears. But if you hold up your phone with a spectrum analyzer, it actually is playing a 10 hertz tone. And you're depending on how tall you are, your body will sort of resonate to that. And you know, military uh, institutions know this very as well as people that want to distribute sound waves around, right? It's not because they don't want to harm people, it's because they don't want people in the way. And the same would be true of electromagnetic frequencies. So it's in the radio range, I think it's about 70 megahertz, something like that. So people don't use those frequencies not because they don't want to harm people. It's because people would be in the way. So if you're on a crowded uh, in a crowded theater, in a crowded stadium, on an airplane, on a bus or a train, and you want to deliver Wi-Fi to everyone, you're not going to use the frequencies that are absorbed by the human body, not because it's going to hurt people, because people won't get their Wi-Fi and then they'll complain. That's the reason that they do it. So we know all this very, very well. Like this is all well understood. And that's the reason why, you know, these things don't exist. Like remember, like these are giant companies with very, very high paid lawyers. And if anything lawyers are good for, it's, reading reading about the science and then figuring out whether or not their clients are going to get sued. So you can, as much as you can trust lawyers, that's why you should trust you're not going to get hurt by whatever waves might be around you. Yeah.
Right. So,
Yeah, so I
so
just wanted to emphasize that point.
yeah. So people who have been making, for example, claims about 5G, they're wrong. Right.
5G goes in the wrong direction. It would actually be like lower frequencies of radio waves that would be bad. Like if they started like, using the frequencies that your microwave uses, that would be bad, right? Um, it higher frequencies are fine, right? Yeah, yeah. Those are actually better than lower frequencies of electromagnetic radiation. Yeah.
So, okay, so then about the Heisenberg's uncertainty principle then.
Yeah, so Heisenberg uncertainty principle. So that was, first thought up by a guy named Werner Heisenberg, German, in 1927, one of the early pioneers of quantum physics, and he, uh, it was kind of somewhat revolutionary, probably one of these big paradigm shifts that at the time classical physics was deterministic. The idea was, there's a physical set of laws that govern the universe around us. Um, there's just a lot of stuff out there. We'll never be able to, know it all, but behind all of it, there's this clockwork universe that's just chugging away. And for isolated systems, controlled experiments, we can use those laws, that framework to predict things. And somehow we were able to step outside of that and decouple ourselves. But Heisenberg came along and said, no, that's not the case. Fundamentally, there are things that we can never know, right? And his example was like he was thinking about, again, at the time, where the problem lied was in trying to describe experiments that were looking at atoms and the subatomic particles. So he was thinking about electrons, and he imagined like an electron and trying to figure out its position. He invented this thing called, it's called Heisenberg's microscope, but he didn't call it Heisenberg's microscope. But he said, okay, well, how would I find out where an electron is? I can't just look at it. It doesn't just tell me where it is. I need to shine light on it. But light is actually something physical, right? It's made of other particles called photons. So now I'm going to basically smash little particles into another particle to find out where it is. Well, I may find out where it is, but now I've somehow disturbed it and sent it off in a new direction. So he did the calculation and found out that you just can't know exactly where something is and exactly where it's going at the same time. Initially he imagined like an actual experiment, some way to figure out where the particle was, and that is what most people take away from that somehow by trying to figure out where something is, you necessarily have to interact with it and then you affect it. And that's true, but that's not the deepest sort of understanding of uncertainty that we have this day and age. Today, uncertainty is understood to mean that there just isn't a reality behind our observations. So when I say particle, when I say position, when I say momentum, these aren't real properties in the world. They're just, they're words to help me describe what it is I'm talking about. But there is no reality behind those things.
Mm-hmm. So, I mean, can we apply any quantum physics phenomena to human behavior or human psychology?
Yeah, so I think there's an analogy there. So there's something called the observer effect, and this in physics can mean the fact that when I go to measure something, I interact with it, and I may, bump into it, or I'm causing some sort of irreversible change to the thing that I'm measuring. The same phrase is used in psychology, but it's also called the Hawthorne effect, and it's basically says if I do like a psychology experiment, but I prime the subject before, then they'll act differently had they not been primed. So if I tell someone what I'm about to ask them about, they'll behave differently than if I hadn't told them. So people try to make that connection. They say, oh, well, that sounds like something in quantum physics, so maybe quantum physics is somehow involved. And then there's some, research papers that apply the same mathematics from quantum physics to psychology, and that's fine. If the math works out and it's helpful and useful, then great. But the problem is somehow now you interpret that as meaning these are genuine quantum effects that are happening to the person, within the person, whatever. And that's just not the case. Now, a good working hypothesis, a good model of the world is that everything, including people, are made of atoms, our standard model, 12 particles and, 6 forces that act between them or whatever the number may be. So some set of fundamental particles and forces that act between them, and that's all there is. So everything we see around us is just built up from these basic ingredients. So that means that human psychology, well, let's say, okay, chemistry is just the application of quantum physics to small collections of molecules. Then biology is the application of the rules of chemistry to collections of biological molecules, and then you just build up, right? Mm-hmm. So from that reductionist point of view, in principle, you would be able to just derive or describe human psychology from the rules of quantum physics. In practice, that's not possible. It may be even in principle if you did some sort of calculation about what the computation that required to do it, it would just be impossible. So we make this arbitrary distinction. Things that we can describe without quantum mechanics, we call classical. Mm-hmm. And then the things that require quantum physics to accurately describe, we call quantum mechanical. But these are just arbitrary distinctions, right? So your brain is made of neurons, which are made of carbon atoms, which are made of these fundamental particles. So in principle, ultimately, they obey the rules of quantum physics, including phenomena such as superposition, entanglement, and they only ever change discretely by absorbing and receiving discrete packets of quantum energy. But none of that matters, right? Because that would never help you in describing the actions of people. Mm-hmm. It would just not be possible to take the equations of quantum physics and put in the billion upon billion upon billions of atoms into those equations and then try to solve them. Like, we can barely solve the equations for like 3 or 4 atoms, right? It's just not possible. So yes, there are quantum effects at play, but not in the way you think, or not in the way you hope, or not in the way someone who doesn't understand what's going on would describe.
Mm-hmm. And do you think that there's anything in quantum physics that people could use to guide their lives?
Maybe. I think it's funny. Yeah. So often I'll stand around waiting for my kids at the playground outside of the school, waiting for them to come out, and I'll talk to other parents. And one of the most common things when the topic of vocation comes up, I'll hear is things like, I hated science in school, or I hated math in school. And often such people have the attitude that unfortunately gets absorbed by their kids, that you can go through life without understanding mathematics, without understanding any science, right? Mm-hmm. And the same is, in the same vein, you can get by, have a successful life, live into your hundreds even, without understanding anything about quantum physics. That's perfectly possible. The problem, I think, is if you understand a little bit, then you're hooked and you need to understand more. That's what happened to me. I think the one thing that quantum physics has taught me, and I think it's probably the most important lesson that I've taken from my life so far, is that we understand the world in terms of models. We navigate the world, which includes a model of ourselves, in terms of fictitious worlds that we place ourselves in. And this is fundamental. There, there is no reality that we have access to. That's what quantum physics has taught me and allowed me to be comfortable with. There exist models of the world, and there's no true model. The how you compare models is through their utility. Use the model that works the best. Um, so, it doesn't bother me that when I want to travel around the city I live in, that I take a map, which is flat, by the way, right?
Yeah.
So it a, a map is a flat piece of paper, has no curvature. It says that the world is flat, but it works really well. Like I'm not bothered by the fact that it's not curved and isn't an accurate, depiction of the Earth, right? Because it works well for its purpose. Now, if I wanted to describe the whole world, I couldn't extend that map out to include everything. I mean, then it would eventually have distortions. But for that purpose, it works well. So you have all of these models, and even within quantum physics, you have certain models. Like I've been saying particles, but I've also told you that particles don't exist, right? So like these concepts work well sometimes and don't work well other times. And understanding that this is fundamental, like there isn't one true model that you have to get at in order to know the truth of it, that such a thing doesn't exist. So quantum physics, I think, can teach you that you know you you should live your life understanding that it's all a fiction, and what you should do is figure out the best one that's going to allow you to navigate the world as conveniently or efficiently as possible.
And getting into another phenomena in quantum physics that we've alluded to earlier, what is superposition then?
Yeah, so superposition is a concept born of quantum physics. It's the idea that when we describe states of the world, so a state is just the information required to make predictions about some phenomenon. So if I say, it has colloquial meanings like my state right now is a bit thirsty, so I'm going to take a drink of water. But the state of a particle in classical physics is its position, its momentum. Some large things have more variables, color, temperature, right? So all the numbers required to accurately describe something so that you could make predictions. In classical physics, the fundamental state is some deterministic thing, set of numbers. In quantum physics, we use different mathematics, and you can add them together. If I take one description, which is like a piece of information, and I take another description, which is another piece of information, and I add them together, like mathematically add them, like take two numbers and add them together to get a new number, then that will also be a valid description of something else. So it just means like there's this kind of structure to all the states that we can describe, and we can add them together to get new states that describe it. Often it's misinterpreted to mean like, oh, if I take a state like a particle's over here, and I take another state like a particle is over here, I can put them in superposition so that they're in both places at the same time. That's not true, right? But you'll hear that all the time. I can take that state and I can add it to this other state, and that will give me a different state that accurately describes some other phenomenon, right? It's not a particle in two places at once. It's something different. We no longer have language that accurately describes it, but the math is very clear, and I can use the math to make accurate predictions.
And I mean, something that we sometimes hear from a few people is that consciousness, our consciousness, can alter reality. I mean, is that true?
Yeah, absolutely. I mean, if I take a rock and I throw it through a window, the window will break, right? What was the cause of the broken window? Well, you might say it's the rock, but I think the person whose window was broken would say the cause was me, right? Um, so as far as our colloquial understanding of consciousness goes, I was the cause, right? My consciousness changed the reality, which was there was a nice crystal uh, forming this window, and now there's just a bunch of broken glass. Um, so, y yes, consciousness can alter reality, but only within the laws of physics, right? Um, Often people add some mysterious, like, non-physical connection to this,
Yeah,
right?
I think that was the issue I was trying to allude to.
Yeah, yeah. Yeah, within the laws of physics, of course, right? But um, if I want to influence something, it has to be mediated by by a phenomenon in the world, right? I mean, we're communicating now through the internet. Part of that appears invisible, right? I mean, the computer I'm using is not a wired connection to my router, so it uses Wi-Fi signals that appears invisible, but there's a phenomenon, there's a medium by which that that is communicated, and it's all bound within the laws of physics. So, it seems like we're having an instantaneous connection, but there is a limit, limited by the speed of light, and light's just so blindingly fast that it seems like it's instantaneous. But there is, if the ping was shown somewhere on screen, it would be probably 200 or 300 milliseconds, right? So, um, uh, yeah, you can, but it has to be mediated through some physical phenomenon. Um, if you think that there's something else that people haven't figured out or described, then you should use the tools of science, like the method of science, to investigate that. To, I don't know if anyone's tried, and probably they gave up pretty quickly if they had. But I think if there was something else to add to science, then we would have seen it by now.
And what about quantum entanglement? What does it mean exactly, and does it change or should change our understanding of cause and effect?
Yeah, so quantum entanglement is like a kind of correlation. So information can be correlated. This happens all the time. Uh, if you send an email, then the you have a sent version of the email in your email inbox, and the person that receives the email, it's perfectly correlated, right? You have the exact same data. But these are letters and symbols that we're familiar with. Um, Within the mathematics of quantum mechanics, there exist correlations as well. So correlation just means, like, if I tried to describe my own information independent of the information that you have, and you try to just describe the information you have independent of the information I have, we won't capture all of the information between the two of us. Like that's true in classical information theory. So in quantum information theory, the way you specify information is with a new set of mathematical objects, and the same is true. So if I have some quantum information and you have some quantum information, and they're correlated, then if we try to describe them separately, we won't capture all of the information that's shared between us. That kind of correlation is called entanglement. So it's just like correlated data, but it's correlated quantum data. Now, that's the simplest, most useful, and technologically actionable definition of entanglement. I think in the physics context, quantum physics has a long, like, confusing history, right? Where it started off as people noticed some anomalies and they tried to, like, correct classical physics, and I don't think that attitude really ever went away. There was always this idea that somehow we're going to, connect it back to classical physics and intuition. And so this language perpetuates. And so a lot of the things you hear about quantum physics, like particles get separated, and when I do something to one particle, it instantaneously affects the other one. None of that's true. None of that is actually in the rules of quantum physics. It doesn't actually happen in reality. It's just that nobody ever stopped to think about a better way to describe it. It's quite, it's not easy. It's quite abstract. Even the word correlation is somehow seen to be a confusing term, even though it's like the most intuitive thing that people can think about. Energy is harder to describe accurately than correlations. So yeah, it's just a set of correlations, but I think it does have some profound implications, right? Within classical like theories, like classical physical theories, we have cause and effect, right? We have forces, and if I want to change something somewhere else, then that has to be mediated through some force, and so that force was the cause of the change, right? More modern notions of causality involve probabilistic reasoning. So, smoking doesn't cause cancer. Like, if I smoke a cigarette, I'm not going to get cancer. When people say smoking causes cancer, it just means that if I smoke, I'm more likely to get cancer, right? It's not like, a cigarette's going to give you cancer. Just means, like, the best way we can imagine giving someone cancer might be to give them cigarettes, but it's not guaranteed. So it's this statistical probabilistic thing. That's already, I think, intuitively, many people get lost at that point. In quantum physics, even that statistical notion doesn't play out. So there are things that happen in the world that I can't describe as being caused by something else using our everyday notion of cause and effect, or even a classical physical notion, or even a statistical notion of cause and effect. So we need some new notion of cause and effect. Obviously, I did something quantum mechanically, and that was the cause, but I can't represent that with classical physics or classical information theory or probability theory or any sort of classical set of tools that I have at my disposal. I need the rules of quantum physics. So it kind of, in some sense, it's a profound change in the way we think about the world, because we try to reason about the world with our intuitive notion of cause and effect. If something happens, it must have been caused by something else. And those are real things that, I can go and manipulate and change if I want to change the outcomes. In quantum physics, it doesn't work that way. But there's just a new notion of cause and effect. You might call it quantum causality. And, I to the best of my ability, I can engineer outcomes that I want by manipulating the quantum information stored in systems. It just requires a bit more mathematics to figure out what I need to do, but a lot more technological finesse. Like in order to see these things, you need a lot of money to build pretty sophisticated experiments.
So I would like to ask you about the idea of the multiverse. Is it just like pop physics, or is there really something to it, scientifically speaking?
So quantum physics is a kind of framework that allows us to model experiments or phenomena. And if we can model it accurately with this framework, then we can predict the outcomes of experiments. And usually the prototypical experiment is like, I have some apparatus, when I press a button, something happens, and then over here at the other end of the lab, I see a signal. I see lights go off, or I see like a little jiggle on my voltmeter. Something happens. I for any experimental procedure you can come up with in a lab, you can figure out a model within quantum physics that perfectly accurately describes such a scenario. Now you ask, well, what happened between when I pressed the button and when the light went off? Quantum physics does not give you an answer to that question, but understandably, people are compelled to ask this question, right? But it doesn't give you an answer. Now, many people have come up with hypothetical answers to this. The problem is you can't verify any of them, not within the mathematics of the theory and not with experiments either. Because if I change the experiment, if I say, okay, halfway between, I think there was a particle and it was doing this. Now I change the experiment and I move the measuring apparatus closer. Well, if I apply quantum physics to that setup, then I'll perfectly predict the outcomes of that experiment. So it leaves this gap, and it says, I think, some people would say what quantum physics is telling us is that there is no answer to that question. It's just not a good question to ask.
And I mean, another.
So I should say,
Yeah.
like the multiverse is one example of, okay, what happened between when I pressed the button and when I observed some result, right? So in order to make sense of quantum mechanics not giving us the answer to what happened in between, people invent all sorts of things. One of them is, the particle takes every possible path between okay, so first of all, there is a particle. That's one assertion, and that particle takes every possible path at once, not in the same universe. There's separate universes for each path that it could take, and that's correlated with an observer in every possible universe. So each observer only observes one location at the screen at the end, where the particle or the phenomenon registers some outcome, and in reality, there's an infinite number of parallel universes, each with a different path of the particle. But there's nothing in the laws of quantum physics that says that this is the case. This is a personal opinion or additional sort of addition to quantum physics, right? That's not necessary, and perhaps not useful.
So I would like to ask you about two more things that could be or not applications of quantum physics, and then a few questions about science more generally. So in science fiction, we see these very frequently, time travel. And I would like to ask you, is it theoretically possible to travel back or forth in time?
Well, I guess the glib answer is you can travel forward in time, and you're doing it all the time. So you know, the second law of thermodynamics um, says that basically time has one direction. And you can think about this from, yeah, statistical mechanics, like that entropy only ever increases.
Yeah.
So, you know, the classic examples are you you can crack an egg, but you never see eggs uncrack. Um, Water spills, but never spontaneously ends up back into a glass. So there is a natural progression of time moving forward, or I mean, we call it forward, right? There's a unidirectional element to time, and we call that direction forward. Um, from an information theoretic perspective, you know, systems contain information that we can extract from them. I can't spontaneously acquire information from a system unless I interact with it. So if I don't interact with it, the information I could obtain from it has to stay constant, or it might increase if I've modeled it incorrectly or if I've forgotten about it. So I can only ever extract information from systems, right? So that again, you know, gives me a forward direction in time.
Yeah.
When you think about it from that perspective, you can't go backward in time. Like it's not possible. Statistically, it may be the case that, say, spilled water will go back into the glass, but that's like exceedingly rare, and that would be a spontaneous event, right? Of course, I can wipe it up and then wring it out, but again, that's can all be described as happening forward in time through my actions and introducing more energy into the system. So oftentimes you hear, like, within the context of general relativity, that you can go backward in time, like you can create wormholes, for example. These things are contained within the mathematics of general relativity. So perhaps that's a possibility within, you know, if you believe that the real fabric of space-time is described by the fields in general relativity, then it's a possibility. But I think it's still considered wild speculation. It's not, and certainly has nothing to do with quantum physics. Like there's nothing that quantum physics adds to this discussion about time travel.
And we've been hearing in recent years a lot about quantum computers. I mean, first of all, what are quantum computers? What's the concept behind them exactly? And are they living up to the hype or not?
Yeah, so I talked about quantum information. I mentioned it before. So it's a new mathematical set of objects or tools that we can use. And until maybe 30 or 40 years ago, it was thought that no matter what mathematics you use to describe information, you could always use zeros and ones, bits, the things that are, you know, in your computer, to equally well describe it. And you know, for the most part, that is true. But if you use what are known as vectors, so these are like lists of numbers. Imagine like a column in Excel. So if I use a long list of numbers instead of a 1 or 0, and that list includes both positive and negative numbers, then when when I add or subtract them, I can get like things to cancel each other out, which zeros and ones can't do because there's no negative numbers in them.
Mm-hmm.
So it turns out that like if I can phrase a computation in such a way that it requires this like canceling out of numbers, then it would be very difficult. It would require a lot of bits to replicate that computation. So if I perform a computation, I can do it by hand with these like lists of plus, positive and negative numbers. Then sometimes I can do it with far fewer steps than if I was required to do it with ones and zeros. Okay, so that's great, but we don't want to do it by hand. We want to find some automated way to do it. So how do I encode these lists of numbers in the physical world? Well, it lines up well with the things in quantum physics. So perhaps I should try those out. And indeed, that's what quantum computers are, right? It's just encoding this type of information that's different than ones and zeros.
Mm-hmm.
It requires, the control and manipulation of like the really, really, subtle degrees of freedom of atoms and light and things at the extreme scales that quantum physics is required to describe. So it's actually a very difficult problem. And we've been at it for 30 years now. Progress is steady, and I would say for me, it's actually quite inspiring that we can continue to make such impressive progress in the control and manipulation of the physical world around us. Mm-hmm. But there's still a long way away. Like there's still a long way to go before we can build a device that can automate these kind of computations that we want to do that existing devices can't already do. But there's no obvious limit. I mean, we're making progress, and progress is steady, mm-hmm. and there's no obvious limit. So eventually we'll get there. But it's just a matter of time. If for people that say, quantum computers are revolutionizing whatever it is today, that's hype. That's not true. Mm-hmm. Like there's nothing nothing useful a quantum computer can do today, as as far as this podcast is timestamped, that I can't do with say a very powerful computer.
Mm-hmm. So, okay, just to wrap things up, 2 or 3 questions about science more generally and about perhaps how people should try to approach, I guess, more carefully some of the BS applications that we talked about throughout the interview. I mean, when people come up with BS that is supposedly based on quantum physics principles or concepts. So, do you think that telling people that they should do their own research is good?
I think it depends on what doing your own research means, right? Like, so we talked about a few of the biases that people tend to be susceptible to before. So if you're going to enter, this research path while ignoring the fact that these biases are common, then probably no, you shouldn't do your own research. But if you're going to approach it critically and try to eliminate all these biases as you go, then yeah, sure, you should do your own research. But I think you have to understand that it's not easy and it's very time consuming. To do proper research takes a lot of time, and you have to be willing to part with your assumptions and throw away all the preconceived notions that you have about what it is you're studying. I think, people use the phrase doing your own research to mean, oh, I found something on the internet that resonates with whatever I wanted to think about in the first place. And that, yeah, I mean, that's just obviously BS.
Yeah,
You
I
haven't
mean,
done research at all. All you did was, cherry pick, you know, you found someone else that agrees with you. That's all you've done.
yeah, and particularly if it is going on Google and searching a particular tendentious question, I would imagine, and then opening up the first link that confirms your bias. That's probably not a good idea, right?
Yeah, yeah.
So, okay, so that's one thing. But do you think that we should tell people that they should believe in science? I mean, is science something that should be believed? Is that the correct way of thinking about it or not?
So I I guess so. Science can mean a lot of things, right?
Okay.
I think often people think that science is a collection of facts that we've discovered about the world, right? That's not really the best way to think about science. So science indeed includes all of the data and experimental evidence that we've collected. And you should absolutely believe, within some, modicum of skepticism that that's true, right? If I say, I went out and I measured the length of a bunch of frogs, and the average length was, whatever it is, 6 inches or centimeters, whatever, then why, why not believe that, right? Um,
Hmm.
but it's not like the issue is like a lot of these experimental facts have to be interpreted in the context of models that we have. So those facts often get distorted, and then you also have to believe that the models are true, and they're not necessarily true, right? In fact, every model that we have is wrong in some sense. Like even our best theory, right? Our the standard model of physics doesn't account for 90% of the stuff we know is out there in the universe. So it's certainly wrong. It's just the best we have. So when we say that, we observe something out in the universe, it it has to be taken in the context of the theories that we currently are using, which we know are wrong, right? So it it I perhaps believe is the wrong word, right? So I think it should be, are you willing to accept these as working hypotheses in order to achieve something? And yeah, if there's a consensus amongst the scientific community, then this is a good working hypothesis. Know that we all understand this in science. And in fact, we're desperately trying to prove that it's wrong. That's what we're out there doing. We're trying to prove that our hypotheses are wrong. We love it when things go wrong because that means we still have a job. We use the word believe just as a simple, yeah, I don't know. It's just easy to say. It rolls off the tongue. It's a common sort of thing, a common shorthand. But that's not what we do, right? A scientist is someone who doesn't believe in anything, but is constantly questioning the assumptions that they have and trying to prove that they're incorrect.
Right. So one last question then, and regarding, for example, absurd claims made by pseudoscientists and sometimes charlatans regarding quantum physics or any other kind of science, do you think that there might be a risk sometimes that people in skeptic communities, for example, or science communicators, by spending time debunking these claims, I mean, sometimes they would be doing some sort of publicity to them. I mean, by exposing people to the absurd claims, they would be contributing to to marketing these ideas and products and so on. Do you think they should be a bit careful about that or not necessarily?
I I don't know. I think I could speculate. I can give you my own like opinion about it,
Yeah.
and I can give you probably somewhere where you could actually test it. So I think most popular skeptics communities are like these little clubs. They're quite insular. Um, and from what I can tell, it's just a bunch of people like creating memes and poking fun at predominantly religious people. Um,
Yeah.
it's not a very inviting place. So unless you want to join in making jokes and memes about other people, so I think it's unlikely that they're really changing anyone's mind. Um, and I I think that attitude of the people within those communities is so extreme that they're not really providing compelling advertising for the communities that they're attacking. Um, so, mm, they're, I think they're wasting their time. Uh, but it looks like they're enjoying themselves anyway. Uh, the, but there are a few skeptics that operate in good faith, but I also think that they're wasting their time because it takes like hundreds of times more effort to dispel some BS than it does to create it. It's simple to create it, but it it requires a lot of effort to go and debunk it. Um, I think I said in the book, just just walk away, right? Um, you, if you don't give someone the platform, then eventually they'll just get bored. So I think the best thing to do is just ignore it. Eventually, these people will get bored and give up. Now, this reminds me of this documentary I saw on Netflix called Behind the Curve, and it was like this documentary about the flat Earth movement in America. And it is, I don't think that it, I, I don't think it either convinced anyone that was on the fence about it in either direction, but one, Netflix is popular. It's like, it's a very popular streaming service. Lots of people, I'm sure, have watched the documentary. So it'd be interesting to see, in that case, if there was a change in the number of people that subscribe to this because of that documentary. And I wouldn't be surprised if it went in either direction. Like, if more people jumped on. And the reason that they would do it is quite simple. You get to be part of a club, and it's an easy club to be part of. You don't have to know anything. You just have to play along with the game, right? So if you feel a bit lonely and you're happy to BS about stuff, then look at that. There's a club you can join right away. It you know not very many people want to join because you have to pretend like you believe a bunch of made up stuff. But if you do that, then you immediately have just made a whole bunch of friends. So I can totally see why people join, right? And it doesn't, some of them aren't that dangerous. It's not like, they potentially hurt themselves or anything like that. So, it, yeah, there's really no compelling argument for the people who are within the club to leave the club because well, they're not hurting anyone, and right, they attach a lot of personal meaning to being within this group of friends. But that would be interesting to see if such a high profile uh, expose of such a thing actually changed people's attitudes towards it. But for the average person, I would say just don't engage. You're just wasting your time.
Great. So the book is again Quantum BS: How to Ruin Your Life with Advice from Quantum Physics. I'm leaving a link to it in the description box of the interview. And Dr. Ferrie, just before we go, and apart from the book, would you like to tell people where they can find you and your work on the internet?
Yeah, sure. So I'm on Twitter. My website is CS, my last name, Ferrie.com. So csferry.com. And you can find links to Twitter and Instagram and all the various social medias.
Okay, great. So I'm also adding that to the description. And Dr. Ferrie, thank you so much again for taking the time to come on the show. I really loved reading your book, so thank you so much.
Thanks, Ricardo.
Hi guys, thank you for watching this interview until the end. If you like what I'm doing, please consider supporting me on Patreon or PayPal. You will find links to it in the description box of this interview. And also, please share the interview, leave a like, and hit the subscription button. This show is brought to you by Enlights Learning and Development Done Differently. Check their website at enlights.com. I would also like to give a huge thank you to my main patrons and PayPal supporters: Per Orga Larsen, Jerry Mueller, Ernst Frederick Sunda, Bernardo Seixas, Olaf Alex, Jonathan Visser, Adam Castle, Matthew Whitting, Bert Arno Wolf, Tim Hollis, Henrik Alenius, John Connors, Philip Force Connolly, Robert Windager, Rui Inácio, Zup, Marco Neves, Colin Holbrook, Simon Columbus, Phil Kavanagh, Michael Stormir, Samuel Andreev, Francis Ford, Tiago Nunes, Alexander Dunbauer, Fergal Cusson, Hal Herzog, Nuno Machado, Jonathan Librant, João Linhares, Stanton T, Samuel Correa, Eric Hines, Mark Smith, João Eira, Tom Hummel, Sardas France, David Sloan Wilson, Yacila Dez Araújo, Romain Roach, Diego Londonho Correa, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pablo Ostazewski, Nelek Bach, Guy Madison, Gary G. Hellman, Saima Afzal, Adrian Yegi, Nick Golden, Paulo Tolentino, João Barbosa, Julian Price, Edward Hall, Edin Bronner, Douglas Fry, Franca Bortolotti, Gabriel Panos Cortez, Ursula Litska, Scott, Zachary Fish, Tim Duffy, Sonny Smith, John Wiseman, Morton Eichland, Dr. Bird, Daniel Friedman, William Buckner, Mau Maria, Paulo Jorge Arnaud, Luke Gloaki, Georgios Theophanos, Chris Williamson, Peter Wolozin, David Williams, Ruf Towell, Diogo Costa, Anton Erickson, Charles Murray, Alex Shaw, Amari Martinez, Coralie Chevalier, Pedro Bonilla, Ziegler, Bangalore Atheists, Larry D. Lee Jr., Old Herringbone, Sterry, Michael Bailey, Dan Sperber, Robert Grassis, Tom Roth, DRPMD, Igor N., Jeff McMahon, Jake Zoll, Barnabas Radix, Mark Campbell, Richard Bowen, Thomas Dobner, Luke Neeson, and Chris Story. A special thanks to my producers Isa Webb, Jim Frank, Lucas Stafiniak, Tom Vanagdam, Bernard Ugni, Curtis Dixon, Benedict Mueller, Vega Giddy, Thomas Trumple, Catherine and Patrick Tobin, John Carlo Montenegro, Robert Lewis, and Alnick Ortiz, and to my executive producers Matthew Lavender, Sergio Codrean, and Bogdan Kanivets. Thank you for all.